Hey there, future engineers. Ready for a deep dive?
Into physics.
You know it. We're going to tackle the
Specifically, that general science section, the physics part.
using our trusty guides.
We're going to break it all down for you
Extract the core ideas, those must-know facts.
and give you some tips to make studying, well, less painful.
Whether you're a physics whiz or haven't touched it since high school.
We got you covered.
First up, mechanics, the foundation of it all.
Our guide lays it out. Properties of matter, motion, forces,
Energy and even gravitation.
the basics of how things work.
Now, something that caught my eye in Chapter 1, dimensional formulas.
It's like physics shorthand.
You express any physical quantity.
Using just mass, m, length, L, and time, t,
It's kind of brilliant.
instead of memorizing a zillion equations.
You break things down to these basic dimensions.
Right.
Velocity is LT length over time. Makes sense. And force is MLT2 mass times length divided by time squared.
See? Not so scary.
And this actually helps on the exam.
Oh, big time. Imagine you're stuck on a question.
About, say, the force needed to accelerate a train.
Dimensional analysis can help you rule out wrong answers.
Maybe even find the right one without the exact formula.
It's a lifesaver.
Talk about a physics superpower. Our guide also talks about rounding off.
Super important for those calculations.
Gotta be precise.
Then there's the difference between scalars and vectors.
Okay, remind me.
Scalars just have magnitude, like temperature.
Vectors.
Have both magnitude and direction, like velocity.
Ah, right.
Got to know that for understanding how things move and interact.
Speaking of motion, we can't forget Newton's laws.
The classics.
Why objects at rest stay at rest.
Unless a force acts on them.
And that whole force mass acceleration thing.
The fundamentals.
Building on that, we get work, energy, and power.
All connected.
How energy gets transferred, changes forms.
Fascinating stuff.
Then there's center of mass.
The balance point.
Key for understanding stability and motion.
Exactly.
And of course, the force that keeps us grounded, gravitation.
Literally.
Why that apple falls from the tree.
And planets orbit stars.
It's everywhere.
A fundamental force.
And finally, in our mechanics journey, satellites.
Not just for GPS anymore.
Vital for communication, understanding our planet.
Speaking of satellites and gravitation,
Yeah.
there's this cool example in the exercise section about a person on an elevator.
Okay.
Asks how their apparent weight changes.
As the elevator goes up and down.
You got it. It illustrates apparent weight.
How acceleration messes with our sense of gravity.
Like when the elevator starts moving up, you feel heavier.
Ah, right, because of the extra force from the floor.
Exactly.
So our weight doesn't actually change.
But it feels like it does because of the forces involved.
Physics in action makes me wonder, are astronauts in space truly weightless?
Good question. But let's move from the vastness of space.
To something a bit more down to earth.
Literally, properties of matter.
Everything's made of matter, right?
So we better understand it.
Mm.
Let's start with two we see every day.
Okay.
Elasticity and plasticity.
Stretching a rubber band, it snaps back.
Elasticity,
And crumpling a piece of paper.
it never goes back to the same.
Elasticity.
Simple, but important.
They're everywhere, these concepts. And Hooke's law.
About springs.
It's not just for springs, though, right?
It governs buildings, bridges, even stuff at the atomic level.
Wow. That's wild.
It is.
There's this graph in the properties of matter section showing load and elongation for different wires.
Important for engineers.
Uh.
Imagine choosing a wire for a suspension bridge.
Oh, yeah. Big decision.
You need to know how the material reacts to stress.
Strength, flexibility, durability.
Exactly. Now, from solids, let's flow into fluids.
Fluids are all around us.
Air, water. Understanding them is key.
So pressure.
Force per unit area.
And Pascal's law. How pressure transmits in a fluid.
Right. Then there's Archimedes' principle, buoyancy.
Archimedes in his bathtub, that eureka moment.
Explains why ships float and balloons rise.
And Bernoulli's principle, something about fluid speed and pressure.
Yes. Explains how airplanes fly and perfume sprayers work.
Physics is everywhere. We can't forget surface tension, water droplets beating up.
And viscosity.
How thick a fluid is, like honey versus water.
Perfect example. And finally, capillary action. How plants drink.
Like a kerosene lamp, the oil going up the wick.
Exactly. Defying gravity.
Pretty cool. Okay, ready to turn up the heat.
Let's do it.
Heat But first, a quick clarification.
Heat and temperature.
Not the same thing.
Right. Heat is energy transfer. Temperature measures the average kinetic energy of particles.
So heat is energy on the move, and temperature tells us how hot or cold something is.
You got it.
Like why a metal spoon feels colder than a wooden one at room temperature.
That's thermal conductivity.
Metals conduct heat better, so they draw heat away from your hand faster.
Right. Makes it feel colder.
Now for the big one. The zeroth law of thermodynamics.
Sounds intimidating.
But it's the basis of temperature measurement, right?
If two systems are equilibrium with a third, they're in equilibrium with each other.
Like my ice cream, my iced coffee, and the freezer air, all the same temperature.
Exactly. It's how thermometers work.
Reaching equilibrium to tell us the temperature.
Such a simple law, but so important.
And as we wrap up heat, we have absolute temperature measured in Kelvin.
And thermal expansion. Why bridges have those gaps.
Will allow for changes in length with temperature.
It's our engineering.
And we talked about specific heat capacity already.
Right, and change of state.
Solid, liquid, gas, the transformations.
Amazing processes.
And lastly, the three ways heat gets around. Conduction.
Direct contact, like a pan on a stove.
Convection. Movement of fluids, like boiling water.
And radiation. Can travel through space like the sun's warmth.
Here we can read about laws of thermodynamics, different types of processes like isobaric, isochoric, also called as isometric, adiabatic, and isothermal, heat, triple point of water, internal energy, work, heat engines, refrigerators, heat pumps, and also about Carnot theorem.
Wow, we covered a lot. My brain feels like it's gone through its own thermal expansion.
Wow. It's a lot to take in, but you're doing great. Remember, it's about understanding, not just memorizing.
Okay, on to the next physics adventure.
Ready for some sound.
Music to my ears. I've always wondered, how does sound actually travel?
It's energy, traveling in waves.
Through a medium, like air or water.
You got it.
So no medium, no sound?
Right, like in space, total silence.
Makes sense. And sound waves those are.
Longitudinal waves.
Meaning?
The particles vibrate in the same direction the wave travels.
Like a slinky. You push it, the compressions and rarefactions.
Exactly. That's the wave.
And how fast does this slinky wave, this sound, go?
Depends on the medium.
Ah, makes sense.
Denser materials, sound travels faster.
So water's faster than air.
Much faster.
Interesting. Now, when we talk about sound, there's pitch and loudness.
Those relate to the wave itself.
How so?
Pitch is the frequency of the wave. Higher frequency, higher pitch.
Like a piccolo versus a tuba.
Exactly. Piccolo's high frequency, high pitch.
And loudness.
That's amplitude. Higher amplitude, louder sound.
Whisper versus a shout. Got it. Frequency for pitch, amplitude for loudness.
You're getting it.
But what about the quality of sound? How come a piano and a guitar sound different even when playing the same note?
That's timbre. It's the unique combo of frequencies each instrument makes.
So it's like their sound fingerprint.
Basically. It's the overtones, the extra frequencies on top of the main note.
That's how our ears tell them apart. Pretty neat how the brain processes all that.
It is pretty amazing.
Now what about echoes?
Reflection. The sound wave hits a surface, bounces back.
And how a room can sound different depending on its shape.
That's reverberation. The sound bouncing around.
The shower concert hall effect.
Exactly. Multiple reflections creating that effect.
Cool. Our guide also mentions ultrasonic waves. What are those?
Frequencies too high for us to hear. Above 20,000 hertz.
We can't hear them, but we use them, right?
Oh, yeah. Medical imaging.
Like those prenatal ultrasounds.
Exactly. And sonar systems for navigation.
Sound we can't hear, but we use it to see. That's wild.
Physics is full of surprises.
Okay.